Hi, welcome to section 8.1. We're going to look at actually getting into chemistry and looking at describing chemical equations. Now, one of the things to look at on this very first slide is a balanced chemical equation that we have right here, where we can see that we have the same number of atoms on the left side and on the right side, 4 and 4. We also are looking at molecules. Those don't necessarily have to be the same, but in this case they are. The amount of moles of hydrogen and moles of chlorine need to make the sense that the moles of hydrochloric acid are going to be the same. And what's most important is that the mass that you start with is the mass you end with. Now be sure to answer these intro questions as always. Give it your best based off your reading. So we get into chemical reactions. Now the first thing that I need you to know is that there are 7 diatomic molecules. They kind of make a 7 and point at the 7th, which hydrogen's that one more. You do need to know these, start memorizing them, start using them. And again, even though this shows the 2 next to it, it really should be as a subscript, as many of you do know. So chemical equations are trying to tell us on paper what should happen in practice. Now, there's a lot of chemistry we won't go into to determine if something will react and if something won't react. That is something that we won't do, but you would do in AP Chem. So we want to focus more pointedly on the signs of a chemical reaction, and we've seen these. Now you see I say possible because I can give examples to where that's not true. So evolution of heat and light, where you've seen it, fires, things burning, things exploding, those are chemical reactions. Where it's not, old-fashioned light bulb. That's just something getting hot. Your toaster, your electric stove getting hot, metal getting warm and glowing. That's not heat or light in a chemical reaction, that's just radiating heat. Production of a gas. Things that we're going to see hydrogen gas being made this semester, and we're going to see chemical reactions where other gases are made. You might have seen this in a volcano of baking soda and vinegar back in your days. Where it's not a chemical reaction is when you open a soda. That gas has been put under pressure, forced into the liquid, and when you open up your soda, the gas is released because of the change in pressure. Forming a precipitate, or quote-unquote a solid, we've seen that several times in the first semester. We'll see it again in the second. Where that's not a chemical reaction is where you would see things like ice forming on a lake, to where solids form. That's not a chemical reaction, that's just a physical change. And then color change. When you saw the precipitates made from clear substances to colored substances, that was a definite color change. Obviously when something burns, it may go from wood color to black because you now have a new substance with a new color. However, where it would not be a possible chemical reaction is when you dye things. Generally, that is an adherence, or almost like a glue, to the fabric, so it appears red when it's still red particles on a white shirt. So those are some examples of physical changes as opposed to chemical changes. When we're in the lab, all of these 4 will be great examples of chemical changes. So chemical equations must have certain criteria. They must meet certain rules. They must contain correct formulas, and what we mean by formulas are these things down here, chemical formulas. So remember the 7 diatomics? If I said methane reacts with oxygen, it must be O2. It can't just be O. It doesn't react with atomic oxygen. It reacts with molecular oxygen. And there's a difference because that's what actually occurs. So these must be true. And if you're given a reaction to balance, you can assume those are true. If you're making your own, well, this harkens back to chapter 7 in making correct formulas from names or other combinations. The second thing is that the conservation of mass needs to work, meaning that how much mass you started with is the same amount that you end with. Now, each atom has its own mass, so essentially atoms need to be equal. That's why when we look down here, we see we start off with 1 carbon, and in the end we have 1 carbon. 4 hydrogen total, 4 hydrogen total. This, I believe, is a typo. This should be an oxygen. Oops. So 4 oxygen, we have 2 here and 2 here. So a total of 4 oxygen. So the amount of atoms and the mass need to be equal. And so we can't spend all day counting atoms, so we'll often take a mass approach, hence the law of conservation of mass. Bonding does change, but not in any kind of pattern. So bonding does change. As we see, we have single bonds here in the methane. These are double bonded. This becomes now double bonded with a carbon. It doesn't mean because it was double bonded before it's going to make double bonds over here. There's no connection with that at all. As we see double bonds here, and then of course single bonds from our water. So this bonding change usually results in heat being released, energy being released in the form of light and heat. Some light we can see, some light we can't, some heat we would sense, some heat we would not. But all of this, the bonding, affects the energy. And that'll be something we'll come back to later in the semester. So, let's look at a word equation. Now, by definition, it's pretty self-explanatory that uses words to explain a chemical equation. Now, it also includes states of matter. I'll circle those. And those different states of matter, we'll see what the symbols are later. But you can see this relies back on naming. If you don't remember the naming, or if you struggled, you need to go back and do review because you will need it going forward. Now, you can't determine bonding before or after because you don't know how things are bonded. You can't balance it because you can't balance the letters that are in the name. You need to balance the symbols. And you can't use for quantitative relationships. I couldn't say if I had 1 gram of barium chloride, how much silver chloride would I need? I can't do that with just the words alone. Now, formula equation, we're getting a little bit better. So I took that same one and we changed it into barium chloride, doing our Ba2 plus Cl minus, crossing our charges. Silver nitrate, silver with its +1, nitrate with its -1. We only need one of those. Again, barium with its 2 plus, nitrate with its 1 minus, crossing the charges, and silver with its 1 plus, chlorine with its 1 minus, and seeing I only need one of those. That's how you get the correct formulas. So hence the formula equation. You also see it includes the symbols used, hence why I included this package here. Drawbacks. It's not balanced, so therefore we can't use quantitative relationships here. For example, we see we have 2 chlorines over here and 1 over here. So if I looked at saying I had 1 gram of barium chloride, how many grams of silver chloride would I get? I can't make that connection yet because there's nothing saying that it's a 1-to-1 ratio. Get used to these symbols. There are several others, but we won't really get into the nitty-gritty of all these different types. But you should be able to pick out these pretty easily. Now, the big difference, aqueous, this is dissolved in water. Liquid is the pure substance as a liquid. Those are 2 different things. So we balance the equation so we have the law of conservation of mass upheld. So I can see this has already been balanced. I'll go through the process of balancing later. But I have barium with 2 chlorines. I'm just going to separate it so you can see it. Then I have 2 silver nitrates. Oops. So I have 1 silver nitrate and another silver nitrate. On the product side, I have barium with 1 nitrate and another nitrate. So you need the correct formulas first, and then silver chloride, silver chloride. So if I were to just go through and cross them off, my 1 barium on this side, 1 barium on that side. Chlorine, 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 chlorine. Silver, 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 nitrate, 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 nitrate. Now sometimes the polyatomic ions will break up into maybe a nitrogen and oxygen or something like that. In this case with nitrate, it could break up into anything. We generally won't hit you with too hard with stuff like that, but be aware of it. I'll show you some techniques that will help it be a seamless, easy process. But this I wanted to show that this is why we balance it, to have the same mass on the left and the same mass on the right, because we have the same atoms on the left and the same atoms on the right. And no drawbacks. We could even look at bonding if we wanted to go there. Alright, so chemical equations. They have some things that they can be used for and things they can't. So, things that they can be used for. The coefficients tell a relative amount of reactants and products. So like here, I have 2 silver nitrates for every 1 barium nitrate. Now that can be handy if we were talking about formula units and particles, but since particles relate to moles and moles relate to grams, I can use also gram relationships, which is more of a practical use. So that can be something very handy that's going to be used in Chapter 9. So get ready, folks, because we're going to start putting this all together. That's what I mean by the relative masses can be done. And this is also true for reactants. So if I was trying to make so much X amount of silver chloride, I could go back and see how much silver nitrate I need and how much barium chloride I need by mass to get a specific amount of product. And so there's relationships between anything in a chemical reaction, and that's the great part about it. What's also true is the reverse reaction equals the forward reaction. Let's say I wanted to make barium chloride. I could use these two reactants, I could use these two products in this case as reactants to make barium chloride. It's not always the exact same process, but the idea here is that if I put heat in, I'll need to take heat out to go the reverse direction. So there is a connection of, essentially, like it says, reverse reaction. You have to do kind of the reverse process. Sometimes it's easier, sometimes it's harder. But the idea is that what you react that make products, those same products can be turned into reactants. Now, there's some things that they can't help us with. You remember that complex chemistry I said we won't get to, but you would in AP Chem? That's about if it will occur or not. Just because you can make it balanced and have reactants in so-called products doesn't mean it's going to actually react. There's rules about bonding and things like that based upon their chemical structure, not because we made up these rules. The reaction may not exist. Same kind of reasoning. Let me go back. About if it will occur, something like hydrogen and oxygen, reacts to make water. But just because you mix these two together doesn't mean it's going to automatically react. It might not do it at that temperature. We'll look at that later in the year. Reaction may not exist is more like the idea of saying, I'm going to say silver and gold are going to come together to make silver gold. There's nothing saying that's going to be true. Okay? Those follow the rules of bonding and other things there. The speed of the reaction. Just by looking at a chemical equation, you can't tell if it's going to happen slow or fast at all. It doesn't help you with that. And how the bonding has been affected. Just looking at this one, you can't tell but just by looking that hydrogen is single bonded while oxygen is double bonded and the particles in water are all single bonded. That can't tell you. You can investigate that with your knowledge, but you can't just do that by looking at it. So it's not good for everything, but it's good for a lot of things, and we'll investigate the things it can't be an indicator for. Alright, so the how-to. A lot of this is pretty straightforward, but I want to make some highlights. If you got water, change it to HOH, especially if you see a hydroxide ion. It'll make things way easier. Keep ions as a whole ion. Okay, if it splits up, then you got to let it go and let it split up. Pretty much read through these. Start with the first compound and its first element and work your way towards the arrow. Makes it easy, makes it ordered, makes it so you're not going to forget or skip over anything. And on occasion you might need to backtrack. That's not because you did anything wrong. It's just that if you have something like oxygen in all four compounds on the reactant and product side, it can be a little hairy and you might have to go back and revise. But that's okay. We'll give you some practice so you can get through it. Alright, so let's look at some examples of using these rules ahead of us. Formula equation, done. No water, done. Polyatomic ions, none. Okay, so let's just start off with our first thing. I have 2 chlorines, all on the left side, total 2 chlorines. On the right side I got only 1. So to make this have 2, I need to have a coefficient of 2 here, because 2 times 1 is 2. Now, yes, I now have 2 sodiums, but don't worry about that. You don't want to ping pong back and forth across the arrow because you often will get lost in more complex ones. So, I'm finished with chlorine. Let's go back to the reactant side, and I have sodium. Right now I have 1 sodium. Over here I have 2 sodiums. So in order to change this to 2, I need to change this to 2. Yes, I realized I have now bromines, but don't go on to that. Do one thing at a time. Sodium, now balanced. Good. Bromine. I have 2 here. I go over to the reactant product side to check. I have 2 there. That's fine. We don't write coefficients of 1. They're just left a line there just to make it a little clearer for you. Let me zoom and get a little better view. All right. Same goes here. No polyatomics, nothing else. I have 2 silvers. I only have 1 silver here. So I need to put a coefficient here of 2 to make this 2. I've always been a strong advocate of writing stuff down. At some point, it's going to just be helpful. It's never going to be harder for you. It's only going to make things easier. Silver's now balanced. I go on to the next element. Oxygen. I've got 1 on this side. I've got a total of 2 on this side. So I see I need to go back and put a 2 here in order to make this 2. So I see that now I have backtracked here. That means this now needs to become 4. And that means this needs to become 4 in order to be balanced. If you ever find yourself going back and forth, just check it again. I see I have 4 silvers, 2 oxygen, because 2 times 1, 2 oxygen, because 1 times 2. Alright, so let's look at this one here. I'll leave my free element magnesium by itself. So over here I have 1 hydrogen, and I have 2. So I need to change this to 2. In order to have 2 hydrogen. As you can see, I'm not changing the formulas. You never change the formulas. You only change coefficients. So hydrogen is balanced. Chlorine. I have 2 chlorines because of my 2 times 1. I have 2 chlorines here. Done. Perfect. I go back to my magnesium. I have 1 over here, 1 over here. I'm balanced. Very nice. Hydrogen. I've got 2 here, I've got 2 here, I've got 2 oxygen, let's put it down here for making it a little clearer. I've only got 1 here, so I need to put a 2 here in order to have my 2 oxygen. Now that changed my hydrogen. I need to backtrack. So in order for this to be 4, I need to have 2 times 2. So 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen. And then this one, I already did that one up there. Don't be silly, guys. These seem pretty simple. They're going to be more complex, but you apply the same how-to every single time, and you shouldn't have much issues. Like I've always said, have a consistent approach to all of these. Those are the people people who find these to be the simplest, easiest, and something that you don't even need to think about as you do many more of these. Come in with your questions. I'll be happy to answer. And again, we can see some more complex examples if you choose. Take care.